Welcome. In this video we're going to go through the P3 revision worksheet as well as some of the questions that may have come up or may have been more difficult to go through. In this, remember that the definition of current is a rate of flow of particles and not just the flow of particles, because we want to differentiate between current and charge flow. The second thing to pay attention to is the units in these charge flow equations. They do love to ask questions wherein there's a unit conversion, either in the time or in the current, or in this case, in both. You'll also need to be aware of which way round your equation is, as you may need to do some changes to the subject of the equation in order to discover what you're actually using. There's a few graphs to sketch and I wanted to go through those with you. If the circuit is following Ohm's law, then that means V equals I times R, and that this will be true for the entire circuit. You'll have a graph of the current as a function of the potential difference, going from a negative potential difference to a positive potential difference. For an Ohm's law following resistor, it will have a true and straight line throughout that entire graph. Obviously in the test you would trace that line with a ruler. However, if you were looking for a diode graph, diodes only allow the current to flow in one direction, and so for one of those options, they would have a nearly infinite resistance, and for the other, they would have nearly zero resistance. And so you'll get this characteristic curve to the graph here. When you're adding up your equivalent or total resistances, remember to determine first if the circuit is in series or parallel. In this case, we had parallel and then series for both of the others, and so we did have to use the parallel rule for adding up the current in a parallel circuit, or the resistance rather, in a parallel circuit. It is possible, though not likely, that you may see a combination wherein there would be a series circuit, so for example another resistor here that's then in parallel with something else. You would start by calculating the series component all on its own, and then you would continue and add that in parallel with the others. But again, this is not very likely to be seen on your exams. When filling out one of these tables, remember to figure out which rule is applying properly. This is a series circuit, and so we can find a total resistance. With that total resistance and the total potential difference, which was known to us, we could then calculate the total difference using V equals I times R. Or in this case, because we were looking for the current, we would have to use the equation I is equal to V divided by R. That gives us our current of 0.1, and we then use that current throughout the circuit because it's a series circuit and the current is the same throughout the circuit. From there, we can use V equals IR in order to discover each of these individual voltages for each of the three components, and you can then check that those add back up to 6, meaning that you've actually got a way of checking your answer in these questions. If you were to sketch the magnetic field lines around a bar magnet, make sure that you label your north and south sides, and that you draw your field lines with arrows pointing from north to south. You will also need to make sure that as you get further away from the edges, your field lines are further apart. If you're worried about the examiner being able to interpret your drawings, then you might want to specify that the field lines are further apart when they're further from the magnet. In this way, you're ensuring that the examiner understands that you understand the concept of the magnetic field as it goes away from either the magnet or a wire. In this case, don't forget that you're applying the right-hand rule and make sure that you've got the correct hand when doing this. The first one, the current is coming out of the page because we're seeing the point, and so our magnetic field will be wrapping around in this direction here, and that would be the same way that our fingers would wrap around if we were going to grab the wire with our thumb pointing upwards. In the second image, the current is going into the page, therefore our thumb is pointing into the page and our fingers would curl the opposite direction, pointing those magnetic fields in the opposite direction. If you're using the left-hand rule, remember that you need to make sure there's this 90-degree angle in between each of the fingers in that left-hand rule, or you won't have your directions correct. In this case, applying it, you have an upwards force in the first instance and a downwards force in the second instance. You can then apply that into your explanation for a motor. So you need to mention at some point that there's somehow a loop formed between these wires, or that a loop of wire is in a magnetic field. And then in this case, we've got one going up and one going down, and that would cause a rotation. And then you need to use that split ring commutator so that when the wire is on the other side of the force, it's connected to the opposite side of the current source. And that would ensure that the wires on both sides are always experiencing an upward force on the left and a downward force on the right, meaning the rotation will be conserved. You can also mention that adding more wires or more current would increase the strength of your electric motor that you've made. That covers all of the questions in this worksheet. As always, if you have any others, please do ask those in the comments below. And in the meantime, happy sciencing.